different particles, right?
What do you, can you see better than me?
No.
I can see it work.
No.
It seems not.
It seems like
Ah, it's recording. Okay. All right. Thank you. Now, even if it's not a Majorana, even if it's a Dirac state, once neutrino has a mass, so neutrino is massive, generically, or neutrinos, right? There are three generations. This would imply immediately the existence of flavor mixing. We will have the analogy with Kabibo situation, right? Kabibo, Kobayashi, Mascava. Okay, so we have flavor mixing. So in other words, we have the leptonic mixing matrix. I have a question which will be in the homework. To count the number of phases for Majorana case, I want you to think whether it's the same, and I won't answer it now. Okay, when we did the counting phases, all I want you to remember, we use the phase freedom in redefining both left and right fields that participate in the quark masses. Quark masses are Dirac type. Neutrinos could be either Dirac or Majorana. Okay. So here, in general, there will be also maybe a phase, one or more, a thing to enter, but this is not so crucial, okay? So, by the flavor mixing, we expect flavor violating processes. We commented on this before. Typical process, which we can come up with. The other day, someone knew, I think. I want to change a flavor, so for example, I want muon to become an electron. So what can I get? I don't want to violate Lorentz symmetry, I don't want to violate charge, I don't want to violate, what is it? Photon, okay. Or, well, for example, this is also okay. It violates flavor because here flavor is conserved and you're going to eat. And you've learned, by understanding the G mechanism, how to estimate, at least how to know whether this is meaningful or not, whether this can have any impact, okay. And we know that the branching ratio for this delta flavor, let's call it, must be proportional to, there must be mixing. Let's think of two generations, okay? Of course I can have tau and so on, but it's not so important. So there will be sine theta leptonic, cosine theta leptonic, something like this square, at least that, okay? Leptonic mixing, by the way, are large, at least some of them, so that's all right. Then, right, because the mixing itself is meaningless unless there is a non-trivial mass difference. And this is at the level of the amplitude we found out. So when we square it, it becomes hopeless, right? This is a terribly small number. This is of the order of 100 GeV. Square it, you get 10 to the 4 GeV squared. This number is the largest mass difference.
10 to the minus 3.
It's in the atmospheric neutrinos, it's 10 to the minus 3 roughly electron squared. We can revisit that a little bit. So this is less, and even if I have, and you know there could be factors, in this case there is a loop factor, okay, or whatnot, okay, I don't care. This is 10 to the minus 3 electron volt squared. What is this? That's 10 to the minus 18 minus 21 GeV squared. See how small it is, to understand the smallness of the neutrino mass, okay, ridiculously small. By 25, so this is less than 10 to the minus 50. Whereas the experiment, the branching ratios of these processes are similar, and they are of the order of 10 to the minus 12, 10 to the minus 13. Remember that this experiment makes it surely less than 10 to the minus 12. Okay. Hopeless. And this we argued, however, this is good. This we like. Ideally, we are very happy when the standard model gives 0 somewhere. You know, this is where you're going to attack the standard model. Okay, this is like neutrino mass. It gave us 0, therefore it immediately opened the way for something new. That means new physics. If I see this tomorrow, it's not a standard model. Many, many people are working in this field for the reasons that I think should be obvious to us. For example, in the example of this left-right symmetric theory, there will be a right-heading neutrino with WR. Therefore, now the branching ratio in this theory for flavor, lepton flavor non-zero, there will be mixing angle. Well, before the mixing angle, there will be obviously something that I could call MWL over MWR to the fourth. Right? Muon decay goes as GF squared. You just, so we have always the usual muon decay, right? So the W. Muon becomes an electron. Nu mu. Mu E bar. This decay rate, gamma mu, is proportional to m mu to the 5th power divided by
M to the
mw.
to this.
Let's call it L to the 4th power with all the factors. So there is automatic suppression of this type, right? This is the strength of the process. This will have to go through the new physics. Okay, this is typically, you will put the scale of the new physics here if it exists. It may be some supersymmetric partner, I don't know, this is just an example here. And then by the use of Jim thing, you will get delta Mn, or maybe we should write Mn squared, or MWR squared, and then sine squared theta, right-handed. There'll be an analog of the left-handed, there'll be a right-handed mixing angle, right? We are not going to compute that, but notice that this could be large. This is sensitive to the physics in the collider regime, in the TV. Okay, take a WR which weighs, I don't know, 2.5 TV, 30 times WL. So I take, just to illustrate, 2.5 TV, about 30 MW, or MWL as I call it. Squared gives me 10 to the minus 10 to the 3, so to the 4th power 10 to the 6. So you see, I'm getting a large number, 10 to the minus 6. I don't know the mixing angle. All I learned that there is some suppression, either the mixing is small. Actually, I am intentionally getting large. A lot of people are claiming that there is a problem, that we should try to worry about that. Now, that a priori we should not. Okay, you may hear people speaking of the flavor problem, and you should take it with a grain of salt. Just to remind you, when I computed the K long, K short mass difference, remember that at the end of the day, there was a factor which was m charm over mw squared. Remember there were various factors? Or in other words, m charm square minus m up square times all the mixings. So for example, this works because charm is light. Someone could say that there is a problem in the standard model, you know, charm should be heavy. Okay, that's a lousy reasoning. There are people who say, oh, this is a problem in this kind of theories because I expect to be of the same order of this. Okay, this is not good reasoning. It's interesting how these prejudices, you know, get accepted. I was just reading last night, before going to bed, late last night, I was reading an article on neutrino oscillation, atmospheric neutrinos, okay? I'll come in a second. So they were actually seeing neutrino oscillations for a long time, but they couldn't trust themselves. These are the fathers of the experiment. Because there was a prejudice at the time. People had a prejudice. that leptonic mixing angle will be similar to quark mixing angle for some reason. Why should there be? There is no whatsoever analogy between quarks and leptons. They are so different in every possible way. After all, they're so different that neutrino, for example, could be a Majorana particle, okay, completely different. We could expect spectrum and mixing angles, okay, there was a priori. So for quite a long time, for years, they were sitting, checking and rechecking to be sure, okay, the prejudice is interesting. And the same authors at the end of the paper says that we have a prejudice today that the new physics here has to be very large. It's very interesting. In the same article, in which we are sort of ridiculing the prejudices of the past, people tend to read that. So I want you to understand that there can be not a problem because the theories do not live at any or at all points in parameter space. They live dangerous. And with the dust centers, they live in one point. Appreciate once again. Then in the standard model, you can get a huge contribution from M top. Very dangerous. You could worry. But it's suppressed by a tiny mixing, theta 1,3, so everything is okay. So presumably something like that would happen, but it gives a hope. Okay, this is the bottom line, that new physics would be there for us to see. Okay. So flavor violation, it's very useful. Lepton number violation here could come from neutrino mass. But then we said, of course, neutrino mass is so tiny that if I see lepton number violation at colliders, this is new physics, for sure. So when people look for it, remember that we said the analogy of neutrino is double beta decay. The analogies of neutrinos double beta decay. What's the process? In which at LHC PP goes into electron plus electron or two leptons plus things that we call jets. And the reason that this is interesting to look for and can probe new physics to very high energies, actually to the very limit of the LHC, because there is no background. The standard model gives a zero background because remember this has to go through neutrino mass, Majorana mass, which at collider energies is negligible. It's a sort of message for all practical purposes. You can always sort of, whatever you do, take neutrinos to be massless, except when there is one or two things that you have to identify that has to do with the neutrino mass. So this is one, if it's Majorana. What about, in general, if it's Dirac? This won't help me. This requires Majorana mass. So what can be sensitive to neutrino mass? Well, neutrino oscillations, you know that. But before that, even more basic. So let's go back to the basics, just to sort of have our feet on the ground to see how much. After all, neutrino oscillations are very indirect. I don't really measure the mass in the kinematic sense of measuring the mass, right? Of using Einstein's dispersion relation. I have this strange interpretation of the data. Well, the beta decay itself, in principle. So when the nucleus decay, or neutron, basically into proton, or actually quark inside, and give us this, the thing is, of course, that you could say how in the world this is going to be sensitive to neutrino mass, right? The energy available there is on the order of MeV, you know, this is, electron mass itself is MeV. So it looks a little not so hopeful. Now, this is what we have actually, a nucleus decays into a nucleus. And to good approximation, you can ignore the motion of this nuclei. Okay, the kinetic energy available here is very tiny in beta decay. Therefore, we could treat this process. You have discussed this? The measure of neutrino mass with Alexei? Do I have to ask him because sometimes there is a contradiction in what he says and what the student said. Let me tell you, I have to trust him. Well, if you did, you forgot then. But let's imagine that you didn't. Okay, so let's try to briefly then, at least gives you an idea how we would do that. So if I wanted to compute the decay rate for this process, I can as well go into the non-relativistic limit completely for the nuclear, right? So strictly speaking, if I want to do the decay rate, this will be proportional to G Fermi squared, this you know. But I don't have to tell you. Then we will have U bar electron and what you have normally is gamma mu L V neutrino, right? Matrix element square you would have. Okay.
No, it's good.
It's okay? Okay. Now, this of course at the same time we have P bar gamma mu. So this is the amplitude that we square L N nuclear, and then we have to take this square. Now, if this guy is not moving, okay, this is going to pick up only gamma 0. The gamma I piece has to do with the momentum on Lorentz symmetry that you know. Okay, when you are, remember, in the non-relativistic limit, okay, then you have the famous small and big components, right, and so on. So the thing that contributes here, this is proportional and real in GF squared. Okay, this becomes a number which has to do with the nucleus. Okay, it's a number of order 1. This I won't compute it. I know it's going to be some quantity which is order 1. So what I'm going to have is gamma electron gamma 0 L V nu bar gamma 0 L U E, and then the sum over spin, right? Then there is D3 P electron 2 pi cube, I don't know, 2 electron energies, D3 P neutrino 2 pi cube, 2E neutrino, and so on, the usual factors that you would stick in, right, if you want to compute that. Okay. The thing here, by using the trace formula, is going to give us, so here I will get some factor here, which I'm not going to worry about. The thing here, what is going to give us, you've been doing this a lot these days, so you may do better than me. This is a trace, so I will write the proportionality, okay? You will see I don't need a precise number for what I want to do. Trace, so P slash electron, gamma 0, P slash neutrino, gamma 0, L. And remember when we had gamma mu and gamma u matrices, I think you've just done it in the last homework. Okay.
Where did gamma 0s come from?
Sorry?
Where did the gamma 0s come from?
Gamma 0 because I'm in a non-relativistic limit, these guys are not moving, so gamma I is not contributing, okay? Gamma I, here what comes out is Pi, when the non-relativistic limit. Which I will take to be 0, basically. An excellent approximation. Okay. And this you computed, I've seen some of you in the last homework. So there are two pieces. There is a piece here with gamma 5. So why not write 1 plus gamma 5, if you don't mind, the privilege of the blackboard. Notice that the gamma 5 will not contribute. I've seen you guys notice that there was gamma mu, gamma nu, that there was epsilon mu nu. Remember, you need 4 gamma matrices different. in order to have a non-trivial trace with gamma 5. So this piece does not contribute. And what we get here will be, I've seen that you actually knew this, when this is the limit of gamma mu, gamma nu. Some of you, if you remember, well, depending whether you've done it in the last homework, I think if you just copied the muon decay, if you try to do it, then it will be very fresh. This is the same thing that the kind of things we ran into the W decay, into top decay, okay? So there will be P. So let's call the P electron P, and P nu let's call K, just for sake of notation to make it a little. So there will be P0, K0. What comes out with gamma mu and gamma nu is P mu, nu, P nu, mu, symmetric sum. Someone remembers this? Plus minus G00, P times K. It's a factor of 4, I think, or it's not so important. Okay, Julian, remember. Well, I've seen that you actually tried to do the, or done the, tried to go over what you guys did. So, it sort of gamma 0 selects. You simply, if there was gamma mu, gamma nu, you could use the Lorentz structure. You would have P mu, K nu, P nu, K mu, it's symmetric. And then it comes out with a minus sign, G mu nu, P times K. And of course, in general, there will be epsilon mu nu alpha beta, which is 0 here. Okay. I pause. I want to make sure that you follow this. So this is proportional. There is 2. So less than this is energy, okay, really. Now I call this E nu minus, this is 1. P times K is E nu plus the P times K, the momenta. So here there will be a cosine theta angle between the okay. I don't need a detail. I'm going to integrate over theta. This does not contribute. If you remember when we did the parity violation in the W decay, total decay rate didn't care about that term, which gave us parity violation. I'll come back to this. All I'm saying is when you integrate d cosine theta, you integrate between minus 1 and 1 because it's from 0 to pi. And this is cosine squared theta between minus 1 and 1, and this is 0. Okay, it's an odd function. So what we get here that the gamma is proportional to GF squared no. Why did I write DE? Sorry. I got E nu. Okay. Then there was in the denominator E nu from here. And then we have D3P is proportional to P squared dP. I'm going to integrate. I'm just interested in the total decay rate, the energy dependence. Okay. And this is P times P dP. Okay. So let me write here. It's better. D3P is proportional to P times P dP. But energy is P squared plus M squared, E squared. Therefore, EdE is proportional to P dP. If I take a derivative. Agree? Or equal. Maybe it's better equal. Proportional would be good enough for us here. I just need the overall factor. Okay. I don't know why keeping GF squared, just to emphasize that. So what I would have P, the momentum of the electron, K, momentum of a neutrino. So by this, let me not have any confusion. These are coming from these. And then I would have E nu, dE nu, dE, dEE. And of course energy is conserved, so I will have the available energy, let's call it E0, okay? The energy difference between final and the initial nuclear states, minus EE minus E. I'm not looking at the notes, so I could be wrong. I don't want to look at the notes. So it's good that you guys check on me.
No question.
Yes, please.
Why aren't you integrating over the Boltzmann momentum?
But I'm taking this guy to be, I could do that, I will do that, but what I'm saying, there will be a number coming out, okay? If I treat it statically, I just have to compute that number. It's a good approximation of what you will get. You can correct it, okay? There will be coefficient that will come out. And that coefficient they actually did, I could cite you in the formula. It's some number over 5 that so I have pi squares and pi cubes. Notice I'm being very cavalier about all the factors, okay? I want to emphasize this energy dependence. If you want, actually I should have actually told you don't worry even about anything else. Let's be more serious. We want to see the energy dependence here of the electron energy dependence. I can integrate immediately over so d gamma over dE electron. Let me call E electron E now. And let me integrate this over dE nu. Oh, I have an integration here, so. Well, no, this was good, sorry. D gamma is this. So if I integrate over E nu, what will I get? So integration over, integrate over E nu, I will get D gamma proportional to P of the electron E nu will become what? E0 minus E. Okay, please, now we cannot get it wrong. So there will be E0 minus E. Okay. There will be E from here. There will be K. What is K? K is integral over E nu squared minus M nu squared. Let me keep Neutrino Mass. I know it's crazy. It looks very tiny. It looks that somehow with all the numbers. Okay, you'll see why I'm doing that in a moment. So let me do that. So what will K give me? Give me a square root of E0 minus E square minus M nu square. You agree? There is E. There was E here.
Yeah.
It did not get cancelled, so it's there. DE. This E is confusing me. Maybe it's there. I need to look up in my notes. Was there some cancellation that I missed? No, I think it's okay. There is E, there is P. So notice that if I want to compute something like d gamma over dE and normalize it by 1 over P and E, it's going to be proportional, okay? There were factors we don't take into account, so just normalize it, okay? There'll be a normalization factor, okay? I can define a quantity which, this I can measure, okay? I will measure distribution of the electron in a centered energy between E and E plus delta E. There is momentum of the electron, energy of the electron. So what we'll have, E0 minus E, and then square root of E0 minus E squared minus mu squared. And typically E0 is written as Q plus m of the electron. Okay, the available energy. This is just definition of Q. Q is the factor that describes the nucleus that decays into this daughter nucleus. Okay, that tells us what the available energy is. The energy difference between the final, the parent and the daughter nucleus. So this is written, and then therefore it means that, and E I can write as ME plus kinetic energy of the electron. It's typically the way they write. So you agree that in this notation this is simply Q minus K, am I right? ME cancels. It's just a notation. And then Q minus K square minus mu square. What is the algebra? Maybe question.
Is KE. Kinetic energy.
Kinetic energy. No, I just wrote EE is my maybe I took the mass out, so the rest is kinetic energy. So instead of this is just a notation used in the book. People that give you, when they discuss nuclei, they give you this Q number, okay? We could just say the electron mass, okay? That's not a big deal. And therefore, imagine that mu is 0. By the way, here, this is a kinematical thing. It doesn't matter whether it's Dirac or Meran, I don't care, okay? Here, mass is whatever you would write when E squared is m squared plus p squared. Okay? That's the definition of mass. That's how I define the mass. Here. The safest definition of mass, this is what you and I want to do that. We don't have a scale. We don't do that with elementary particles. But we probe their masses through their dispersion relations. Okay. So what would I get? I will get this quantity here. So let's call it f of E. It's some function of E that I define. This f of E, properly normalized, would just be, actually what people take is the square root of this. Okay. This is f of E. What people plot is the square root of f of E. How would it go? This would be 0. And the square root will just be Q minus K. You want to emphasize this linear dependence on the kinetic energy. So you plot this quantity, which you have to compute here. There is non-trivial factor of nuclear physics that I ignore, the kind of questions you can ask me, and all the details of the nuclear physics, okay, normalization constants, that we can read up in the books, okay. What we did correctly and carefully is this dependence. Therefore, this would look something like this, and this would hit here if this is a kinetic energy, and this is the square root of f. This is called Curie plot. I would hit this when this is equal to Q. What would happen if mu is non-zero? You would hit it before. You wouldn't get it. And of course, when will it matter? So in other words, when will you hit it? So these are two cases, when Q minus KE is mu. So in other words, KE is Q minus mu. Call it K0, this point. So it's going to hit it here. I'm enlarging this, where this is a water, this is Q, this is a water neutrino mass, you agree? And if you go like this, in the beginning, okay, this becomes, of course, appreciable when I'm near the end point, when I'm there. So it goes like this, sort of, let's, okay, this is a hypothetical thing. And these experiments, people that do this, okay, this is extraordinary hard, non-trivial, how to interpret, how to do, there are all kinds of problems you can imagine of nuclear physics, okay? All kinds of details, and you have to have extraordinary resolution, and the things that you look for is the nuclei with the smallest q. That turns out to be tritium. So people that do these experiments have been using tritium for a long time. Tritium has Q 18.6 keV. This is ideal, smaller even than the electron mass, obviously. It's very small. So therefore, if a neutrino mass, let's say where of the order, if neutrino mass were of the order of 10 electron volt, this was 18.6, this would be 18.59. Okay, this is, we have to be occasionally there were experiments that claimed that they saw something, okay, and people would get very excited, and then other experiments, there are a lot of experiments in Mainz, in Livermore, in Los Alamos, in a lot of places that are settling that, you know, in spite of the uncertainty and so on, what is emerging, that you can read everything, the neutrino mass, everybody would agree with 3 electron volt, and I've seen actually most of people saying even maybe 2 electron volt. Okay, so I think if I write less or equal 2 electron volt, no expert would object. It's interesting that the limit is similar to the limit because it's nothing to do with this neutrino double beta decay. There are these strange conspiracies. Right, the other thing has to do with the strange lepton number violating decay. Here we are looking at the end point in a completely different nuclei. There they are large nuclei, okay, with a lot of protons and neutrons, right? Tritium, after all, it has only 2 neutrons and 1 proton. It decays into helium-3, which has 2 protons and 1 neutron. And we have to wait. As usual, neutrino physics, as Pauli said when they announced in 1956 that neutrino had a mass, when they told him, sent him a telegram, and says, everything comes to him who knows how to wait. Neutrino physics is all about waiting. Somehow, if you like neutrino physics, you have to be patient. You wait 10, 20, 30 years, right, before the results emerge. There is a countering experiment in Germany, which is the state of the art, which apparently can push, okay, this is our great hope, the new generation experiment, this by an order of magnitude. Which at the same time, there are a number of experiments, as I've been telling you, a lot of them called Gerda, Nemo, Mairana, Cuore, looking for neutrino double beta decay. A lot of them in Italy here, in the Gran Sasso Laboratori Nazionali, in other places also, in the Mediterranean. It's an exciting time to wait. But what will happen, we don't know. Unfortunately, there was a time some 30 years ago when everybody was excited waiting for proton to decay, okay? Life is ironic. And people that look for neutrino oscillations would hide into the experiment that look for proton decay, because basically these are one and the same type of experiments, right? You need this underground swimming pools full of water, which you look either for for this. Now today you cannot get easily money for proton decay because life is like that, but neutrino oscillations are of course very exciting, so people that look for proton decay are hiding in the experimental groups for neutrino oscillation. And the irony may be that looking for details of neutrino oscillation we may discover proton decay, which to me would be more exciting than yet another detail. Okay, I'll speak a little bit about details. This is of course not the detail. Us seeing really the actual measured value of neutrino mass would be what you and I are after, right? As particle physicists, not just indirect. And this is measuring neutrino mass. This is not neutrino double beta decay that could come from new physics. This is coming from neutrino mass. This is just kinematics, right? You know, it doesn't ring the bell. You didn't discuss this.
He mentioned something.
Oh, he must have talked a
He
little bit.
mentioned the endpoint and investigation.
Ah, he did, okay,
He
but
did
maybe not to this
before.
detail you were saying. Okay, then I'm glad that I sort of decided at the last moment yesterday preparing the even if you don't do the muon decay, if you didn't do it, you're just trying to do it, you know, the more often you do it, these things become very familiar, okay, and you can sort of just you stop doing calculations, you can write them down. Okay. So this was not seen, so we should talk a little bit with what was seen, which we discussed with Smirnov in detail apparently, so I'll just remind you, okay, but before I move on to obviously what I have to move on is oscillations, okay. And we'll see how we were lucky with oscillations when the numbers come out right. You know, these are things in life and the numbers don't want to come, okay? You have a great experimental effort with great people that understand and do this beautiful analysis, which, you know, you have to be an artist here, okay? Incredible sensitivity of things that you have to worry about, okay? The numbers sort of conspire against you. Okay, before I erase it then, the reason why we speak of neutrino mass is neutrino oscillations, and so maybe it's good to remind us of how it all came about, neutrino oscillations. Why we actually think that there are oscillations, really. So let's see how much you remember. When the other times when we sort of chatted, it seemed that you had pretty good memory from what Alexei was telling you. So what happens? I get cosmic rays. And cosmic ray is basically what? What do you think are cosmic rays? 90 or whatever, 95%, 98%. I can't speak with authority or passion on cosmic rays. But we all know they are protons. They hit the atmosphere and they produce pions. They may occasionally produce a cation, but they mostly produce pions. Okay, pions are very interesting. So I may get P minus or P plus, and that decays into mu minus plus nu mu bar. It practically does not decay into an electron. This you knew, right? There is a mass suppression. This, of course, decays into the electron. So minus plus plus other neutrinos. Okay, why don't we write that? So if I want this notation, then this is nu bar. Let's keep 1. And the same for plus. So this will give me an electron plus nu E bar plus nu mu plus nu mu bar. This together. So you see what I expect? If I don't want to distinguish between u and u bar, okay. After all, in order to distinguish, I mean, how do I see neutrinos? Neutrinos have to hit the target, which is my experiment, and then produce muons or anti-muons to produce back. If I don't distinguish the charge, then this is the same particle for me. So, super Kobayakande, this is a super Kobayakande experiment. Kamioka mine in Japan. I think around 250 kilometers from K laboratory. An impressive 50,000 tons of water. Does not distinguish. P from P bar. Particle here, it's not a proton. It does distinguish flavor, okay? I can distinguish electron from the muon, even if I don't care whether I produce the positron or the electron. Okay? So what do we expect, you and I? That we'll have about the double of the flux of nu mu compared to the flux of nu e. Okay, respect. Flux nu mu. So by nu mu I call generically now particle plus antiparticle, okay? And the rest of what I say is about twice the flux of nu e. Now why do I say about? Okay, let's think why I say about and not exactly. Because from what is written here, there should be practical. Factor 2. I can erase this. I think it was clear. I'll send you some notes, and I'll tell you where to read, actually, this. By the way, I can say right now that probably still the best book on neutrinos. I don't know if I mentioned this book, is Mohapatra and Pal. I told you that the book of Palash Pal on Introduction to Particle Physics is kind of pedagogic and useful. But they have a book of neutrinos, on Neutrino Mass, Mohapatra and Pal. Chapter 12 is what I've discussed today. Now, the neutrinos, in other words, if this is Earth and I have my super Kamiokande experiment, okay, there is a guy sitting here observing neutrinos that come from the sky, and these neutrinos may come from above her head, okay. They may come from all the way here. They may be coming from somewhere here, and so on and so forth, right? They come from all kinds of directions, okay? And they should be observed, and the profound difference between these two is the length of travel. So typically this production of pions happens around 10 kilometers, okay? This is where this place is taking place. Muons are produced at the height of about 10 kilometers. So the guys coming from above travel only 10 kilometers. The guys coming from below travel what? 13,000 kilometers, right? Here we have about 13,000 kilometers. And I can look at all possible variations, and that means I can talk what is called the zenith angle, right? The angle that goes from 0 to pi. And the, or from minus. So what happens, of course, when muon, what is important to note is that muons need time to decay. the mu lifetime is 10 to the minus 6 seconds. When it's at rest. Which is what is 10 to the minus 6 seconds? That's about 10 to the 4 centimeters, right? Now it depends, of course, with what energy they come. So here they look of all kinds of energies, the sub-GeV energies to very high GeV energies. The flux of neutrinos goes down with the energies. So most of the stuff that we'll talk about are the energies of the order of GeV. A bit bigger than GeV, but in this range. So when the energy is GeV, of course, mu will travel more. And we can put a number, so why don't you try to put a number? Tau mu actually is what is it? I think it's about 10. Okay, what would I get if the energy is GeV? That's about 10 times the mass. So what will the lifetime be? So 10 to the 4, this is 10 to the 4 centimeters. What is 10 to the 4 centimeters? This is 100 meters, roughly. There's a factor of 3, I think. 300 meters. So take the energy of which is of order GeV, you get a factor of 10, roughly, in the lifetime, right? Dilation factor, energy over mass. So for energy of order GeV, so this is at rest. So tau mu with E equals GeV becomes about 3 kilometers. So if they have an energy a little bigger, you see, they're getting to about 10 kilometers. They may not have time to decay all of them. You have to take all these sort of subtle details into account. For example, the guys that are coming from here, they have the time, and they will decay. So there, for example, I expect a factor of 2, precisely, if they have to travel more distance before hitting the Earth. Okay. So it depends how they come. Okay. But roughly, you and I can take this roughly, this thing. Now, what we should remind ourselves, what is the probability for oscillation? This you derive, nu mu, into something, let's call nu prime, I don't know what it is decaying into, will be sine squared 2 theta, sine squared delta m squared L 4e. Why don't I anticipate here? Nu tau. It took quite some time to figure out that this is nu tau. First thing, they realized it was nu e. They started to see, so in other words, what I need here, actually I don't, no, sorry, P nu mu, assuming that the two generation approximation is good, and we'll come to that in a second, okay, just assuming, the survival probability is 1 minus this. So let's write this is safe, then we'll think what is oscillating. So what they saw is when they look above, they saw more or less what they expect. Okay, you compute the flux. Anyway, it's relative. You may make a mistake, but this computational flux took a long time, and they have done with a great precision. So you have the formula. I think it's about of the order. The flux for GeV is of the order of less than 1. It's surely less than 1 per centimeter square per second, or on the order maybe 0.23, okay, for GeV energy, okay. GeV energy somehow was ideal. If I go to very high energy, the flux becomes very small. Okay. With high energies, I may have more interesting effects by the energy. So, what they started to notice that as the distance increased, the neutrino had to travel. The flux kept being reduced. And they actually managed to see with a lot of time, they took a lot of time. You see, when they were saying neutrino oscillations, people told them, well, you know, you shouldn't expect anything because the mixing angle should be very small, like with the quarks, and then forget this. It's going to be too tiny to be observable. And they found out, and this is a beautiful thing, they got a dip. They found out that actually oscillation, let's try to compute the distance. Well, we won't do that, we'll do the opposite. They found that at a distance about 500 kilometers, they got a dip. In other words, when this is over pi over 2, I get a suppression. Two things very important here. You want to see the pattern of oscillations, you want to see this dip. And this is appearing at around 500 kilometers, okay, this is the first statement. We put the delta m square in a moment. So roughly for us around 10 to the 3 kilometers when we estimate the numbers. When you look at the neutrinos coming from here, in which they have many oscillation lengths, okay, so they keep oscillating. What you do in this case, you average. Okay, because there's going to be a number of oscillations that you don't have a fine resolution. They don't measure energy with great precision. Okay, so this is the dip at this distance, whereas P, nu mu surviving, coming from below, so let me write like this, will be this with the oscillation pattern average. What is the average of sine squared? 1/2. Or sine squared, sine squared. So you should expect 1 minus 1/2 sine squared 2 theta. This you can do only if you establish that the oscillation length is small relative to the Earth diameter. Okay. So here again you see the numbers favor this. Why? Because I can immediately, depending what you tell me, I can tell you what sine squared 2 theta is. They got here a half. A profound effect. Not some small loss of nu mu's. They lost half of the nu mu's coming from above. This is from the core of imagine that will happen in the sun, and people kept observing. Davis in the old days and so on. In the atmospheric neutrinos, okay, it was easier to establish the oscillations because you can vary the length easily. What this implies? The theta is 45 degrees, roughly. This stupid prejudice that let people waste years. Okay, it's nice to see it was completely wrong. By the way, I want to emphasize that in the standard model, this prejudice really doesn't make any sense because I have no connection between leptons and quarks. They have the separate weak interactions. They don't interact with each other. They have the separate Yukawa couplings. They have separate patterns of masses. Neutrinos could be even Majorana particle. To imagine this correlation is insane. Now you could say, but I love, now this is, of course, a tremendous speculation. Suppose you say, but I love grand unification. I want to see what happens in grand unification. You say, there, you say you put quarks and leptons together. That's the idea of grand unification. Remember what I told you. You put together weak and strong interaction, quarks and leptons. So you say, aha, there I expect the same thing. But I also told you that the scale of grand unification has to be huge. You have to break the symmetry between quarks and leptons immediately. Proton stability told us. I'll remind you again in due time. But please remember that we argue that the scale has to be huge. So therefore the symmetry between quark and leptons is broken at such a high energy that no trace remains. And it was interesting in some of the examples that we worked out with my collaborators, most of them at ICTP, most of the work was done with borrowed bytes and others. We actually found some examples that you could compute that of grand unified theories. And we actually found out that the small quark mixing angles wanted a large leptonic mixing angle, because there it's correlated. So there was no reason for this prejudice. I hope you understand it. Once I know the mixing angle, you see now it all fits. I can determine delta m squared. I see here a dip. I think the fall in the, when this is pi over 2, right? So from the dip, I find out delta m squared is 4e roughly. No, let's say the order. Okay, what I would write, delta m squared L over 4e is pi over 2. This is the first dip, right? When this is maximum. And I would estimate, okay, that delta m squared is E over L. After all, I'm not giving a precise number for energy, and I'm not giving a precise number for L. Okay, I said this is roughly order GeV. Let's see if this makes sense. If not, let's forget it. If we cannot get the rough number. What is a kilometer? That's 10 to the 3 meters, right? And a meter is 100 centimeters. So kilometer is 10 to the 5 centimeters. So this is 10 to the 8 centimeters. Now I remember this. I wonder whether you, one number I sort of remember. This is the inverse GeV, the size of the proton and neutron, right? In our units, okay. Lengths and mass, all of that. Almost the same units. GeV to the minus. Do you know how big proton is? How big is this?
It's 10 minus 15.
Yeah, actually it's not, it's a little bigger. It's more like 14.
14, yeah.
Actually it's even bigger than that. It's some number. It's 10 to the minus 13, 10 to the minus 14, okay? I don't know. I think it's closer to 10 to the minus 13 centimeters. So that means that the centimeter is what? Is 10 to the 13. So this is GeV. This is 10 to the 8. And then the centimeter should be roughly 10 to the 13 if I'm right. I'm going to take 10 to the 13 because it's a factor of 2, 3 times. That's how I remember it. And the centimeter is, what is this? GeV to the minus 1. Am I right? Please, let's make sure that I don't move here. So this is 10 to the minus 21 GeV squared. Comes out roughly okay. But you see, okay, it's not precisely 10 to the minus 13. I should just expect to get them rough there. This is 10 to the minus 3 electron-volts. So see what you see, Swallow. You don't even see here very well what it. The way I discuss it here, I don't know what is happening. I just know that nu mu is disappearing. And you try to take other explanations into account. People suggested everything, decays, violation of Lorentz symmetry, whatnot. Okay, all other explanations failed. I'm not going to go into that. Okay, this is a typical example when before you have a direct multi-proof of some theory, you start believing it by eliminating other explanations. Like you guys speak of dark matter. And there are still people, okay, I've seen that this is already, you know, it's so popular that it's there. There are some people that say, well, you know, I can't speak with authority on this. They say, no, there is no dark matter, it's just gravity ought to be modified at such and such scales, okay? And then the people object that this doesn't work. It goes back and forth, okay? But by and large, most people then start to be convinced that the other things are failing, and there, of course, there is a danger of prejudice. Okay, here there is absolutely no discussion anymore in the community as far as I, as a non-expert, follow. I don't think there is by any chance a conclusive evidence of a similar type for solar neutrinos when we speak of oscillations. You know, speaking their oscillations is much harder because you're not going to vary the length of the distance of you and I from the sun, right? And anyway, the process seems to be that they oscillate in the sun. So, I'll dig out a plot. I can send you the plot, okay? Well, this is in various reviews and views, but I'll send you a plot just so we can look at the plot together. I don't have it here. Of the flux of nu mu being diminished and varying from here. So no oscillation here, so remember, no effect. Maximum effect. And this is the distance of roughly 1,000 kilometers, the dip. So what is, they could conclude at least it was not oscillating into nu E. There was no excess on nu E whatsoever. They actually, for superconductor, it's not easy to see nu tau, you know, you have to produce tau. Tau lives very short, it decays and so on. Yet they would argue that to some, you know, they use this sigma, you know, the probability for the event that we defined at 5 sigma in the case of discoveries. It was much smaller probability, it started to look like nu tau. It could have been some new neutrino. Imagine if it's neutrino. Maybe there is some what we call sterile neutrino. Maybe there is something which does not interact with the Z boson. There is always this question, are there more neutrinos? Well, you guys know there cannot be more neutrinos of our type. Z boson decay bits will change immediately. We measured it very well. But there could be some of these sterile guys, you know, this right-handed guy that they introduced by hand. Who knows if that guy actually is very light? A priori, I can't argue. So here the big issue was what is nu mu oscillating into? And the way to answer it, of course, they started to see nu taus, and then of course you do long baseline experiments, which are the first thing they did was K to K experiment. You see this distance of roughly 500 kilometers is very good. Now I can do the experiments on that order of scale, right? So this one didn't have precisely that number. This is from K laboratory that produced neutrinos. Neutrinos travel to Kamiokande, and the distance is about 250 kilometers. And the advantage is there that you have a clean nu mu, you measure the energy very well and so on, and you can see the beginning of the, this was the first experiment, and you can see what it goes into, you will get that excess of nu tau. Then there is a Minos experiment, which went after it, I think immediately, very soon. And this is, you produce the guys at Fermilab. And then they traveled to a detector mine in Minnesota. And here I think we talk about 700. A good distance, this is bigger. I can go over 500 kilometers. About 700, I don't know, 50, maybe 35, 40 kilometers, okay. These baseline experiments are of course very important. With those experiments we can confirm that nu mu is going into nu tau by having a controlled experiment. And you keep doing more and more of experiments by changing the distance to see oscillations, so now which is becoming more and more convincing. Now the question is, the fundamental question is here. How could I pretend that there are only 2 generations? There are 3 generations. So why is it that this works? Actually, it works to a very good precision, okay? There is. That meanwhile, what was important, you know, after this great success, people sat down even more, and the solar neutrino experiments indicated the disappearance of nu E and the excess of nu mu in the sun. With the delta m square about 10 to the minus 5 eV squared. Now look at this line. It's completely different from the other one. And this is very useful, the fact that I can separate them very clearly. Okay? It will be very confusing if they're similar. Okay? And then how would I do that? And moreover, here this is theta atmospheric, about 45 degrees, and theta sun, about 30 degrees. Again, fairly large mixing angle. Again, the prejudice of small mixing angles, completely wrong. Analogy, this is second and third generation, remember, theta 2, 3. I told you it's about 10 to the minus 4 for quarks. So, 2. Basically 0. This is the first and the second generation. Well, this is not so bad. Theta 1, 2 for quarks is about 13 degrees. Well, yet appreciably small, especially with the right sign squared. Theta. Right? This is a quarter roughly. In the case of Cabibbo, it's 1 over 25, okay, the quantity that measures the physical process. It's not the mixing angle, it's the square of the mixing angle we found out. And it turns out that the 1-3 mixing angle, people were not finding direct evidence for 1 and 3 mixing angle, and today it's known that this is very small. There is theta 1-3 mixing angle. How would I call it? The analogy. So let's forget the quarks. This I could call theta 1, 2. This I could call theta 2, 3. 2, 3 generations, 1, 2. Theta 1, 3 is maybe 10 degrees, around 10 degrees. It's fortunately small. Okay, so the next stable approximation works very well. You should now sit down and you should do the 3 generation pattern. And fortunately, the effect is very small. I'm not going to do it. I don't want to write down the 3 generation oscillation. I mean, it has to be done. Just don't want to do that. We don't need it at this picture. So there is a little analogy with quarks, right? That somehow you like to mix with your neighbor. But here you mix strongly. Here it doesn't even make sense to speak of a species. It's 45 degrees. It's the maximum mixing. Okay. What is missing? Well, what is missing is neutrino mass. The scale of this thing. There are 3 states, and we know one mass difference square, we know another mass difference square. So the burning question is, how degenerate are neutrinos? Are their masses close to electrovolt and their mass differences are small, or they follow a hierarchical pattern? Okay. If you wish, this has to do with the neutrino hierarchy. This is a Bedley rating, okay? This is the holy grail of neutrino physics. And it's somehow related to not somehow, it is related to what we talk about, to the direct measurement of neutrino mass, okay? What we know, tell me the lower limit of neutrino mass whatever it is, whichever particle it is, one of them has to be bigger than from what is written there. The square root of this. Right? It cannot be smaller than that, otherwise the mass difference would end up being smaller. So it's bigger than the square root of theta, of delta m squared atmospheric, which is roughly what, 1 in 30. And I think the correct number is 1 over 25. You see, when I cited, there must be some coefficient here on the order of 2 or 3. So this should be roughly 1 over 20 or 1 over 25 electron volt. So again, it's a question of luck. If the mass is so small, then the direct thing is well, here again there is mixing. Okay, so fortunately, in the rate I may have the mixing with the other neutrino. It turns out the neutrino mass is too small to be the dark matter of the universe. So that won't have this dramatic impact that when I started my PhD, there was a hope that neutrinos could determine the fate of the universe. So if you love neutrinos and neutrino mass, it was even more exciting. Okay, the number is too small. How would you and I, how would we figure that out in the next few minutes? Okay, or relax chat. So let me stop here as of what I want to say about neutrino mass. How would we know how big should neutrino mass to be the dark matter? How could you and I know how many neutrinos are there in the universe? That little cosmology that you learn. You didn't talk about the neutrino sea yet with Paolo. Yeah, he said, I think he told me that it was unlikely that he was going to find time. So that just gives you sort of a glimpse into how this would work. Okay, this is a telegraphic chat. Just relax. Don't have to learn anything here. I must be frank, you know, I have never worried too much about this pattern of oscillations. I'm after the origin of neutrino mass. I want to see what neutrino is made of. I want to see what I want to see. So I find this maybe not so fundamental details, but of course they will be crucial. You see, measuring these numbers, of course, will be the test of the theory that tomorrow will emerge, if it has not yet emerged. For all that we know, it may have emerged. So how could we guess the, what do you know of cosmology? What did you learn with Paolo? People ask you about Big Bang. What are the central things you've learned? How would we try to? Well, that the universe gets younger, it gets hotter. So let's say what you know. You know that, for example, a Hubble expansion of the universe, when the universe is quite hot, when it's radiation dominated. Do you know how it became? Depends on temperature. It has to do with the density of the universe. When the universe is very hot, how does the energy density? T to the fourth. That's Stefan Boltzmann law, right? It's T to the fourth. That's the only scale. H squared basically goes as rho. Right? There is G Newton there. So H goes as T squared over M Planck. So I know the expansion of the universe when it's hot. So Just to summarize this you've done with Paolo. So once upon a time, when, okay, on the other hand, I need to know the decay rate for processes. And the particles are interesting are neutrinos. So neutrinos, when the universe is very hot, how they are kept in equilibrium? What happens to them? Well, for example, neutrinos can interact with the Z boson and the electrons. Or W, or electron neutrino, up and down, and so on. But this is there for sure. So if I ask you what is the decay rate for this, would be GF square, right? Times, I'm going to very hot universe. T2, T to the 5. Aha, so you know that, I'm glad. At high temperature, and I'm assuming here temperature bigger than MeV, or bigger than 0.5 MeV to be precise, right? This is what I mean by hot, because otherwise I have to worry about electron mass, there is a scale. But when the temperature is bigger than so when is the guy in equilibrium? When the decay rate is bigger than the expansion rate of the universe, you have an equilibrium. So when do they get out of equilibrium? So the freezing of neutrinos. Freezing of. When does it happen? When these two are equal. T critical over M Planck is roughly GF squared, T critical cube. And notice what I'm doing, okay? It's a miracle if I get it right, but I'm taking all the coefficients to be 1. Here there is, I don't know, 192 pi cube. There is a coefficient here, it has to do with the number of species. Okay, I can't do that, I just want to give you a rough idea, but you know this, the freezing of this. Why not I put cube? Fifths, if you, sorry. You see, I'm anticipating, thank you. This should be cube. So the critical temperature is GF to the -2 over M Planck. Okay, cube, let's write the whole thing. What is this? This is 10 to the -5, so this is 10 to the 10. 10 to the 10 GeV to the 4th. M Planck, remember I told you, is about 10 to the 19 GeV. So I get 10 to the -9 GeV cubed. So the critical temperature is roughly MeV. So the formula is pretty good, okay? It turns out when the dust settles that this is, I was lucky, okay? This is one of the examples when you are lucky. I can tell you examples when you are not lucky and your estimate is badly off. So that means when that temperature, neutrinos were in equilibrium. So that means that there were as many neutrinos basically as anybody else. And who was around at that time? Time. At this time. By the way, this is time. I can compute the time when it happens. It's got to be around the second, right? Am I right? Second? More or less? Okay, thank you. Roughly a second. Who was around? Well, all the heavy species basically decayed. The people that were around was electrons and neutrinos. And photons. So you see, if I go back to the time around the second, there are as many neutrinos as there are photons. Remember, there is a spin dependency, okay, that Paolo derived for you. You've done this carefully. But the bottom line is that there is almost the same number. So what happens afterwards? Well, electrons and positons annihilated, and they increased a little bit the number of photons. So there are a bit more photons than neutrinos, but that's basically irrelevant, right? There is this huge number. And let me see if you know how many photons there are in the universe? What is the number of photons? It has to do with the photon temperature, which is 2.7 Kelvin, right? How much it gives you for density, which goes as dq?
410. 400.
On the order of 110 grade per cubic centimeter. By analogy, there is a neutrino temperature, which is not 2.7. There are less of them, so there is a lesser temperature. And I think it comes out as 1.8 or something, okay, or maybe you've seen it, which tells you that the number of neutrino per species is about 130 per cubic centimeter. You get something like this. But there are 3 species of neutrinos, so the number of neutrinos is roughly the same as n gamma. So there are, just as more or less, you're still with me for another 2 minutes? So I know the number of neutrinos in the universe. The only other thing I have to know, well, I have to know, are they the dark matter or not? How would you and I decide whether they are the dark matter of the universe? Well, how much matter there is in the universe? How to remember that?
25%.
A better thing is, what is the number of baryons? For example, divided by the number of photons relatively. This is one number you should know in cosmology. Well, 2 numbers, I don't know. It's good to know this number or this number. You can go from one to another. But this will be important that you guys know. Do you know it?
10 to the minus.
It's small.
Yeah.
The universe is basically empty. There is no matter. But it matters a lot because it's heavy. It's very funny. Now we'll see how much. So what is the...
It's a minus 10.
Okay, 10 to the minus 10, great. So if I calculate the energy in the form of baryons, compare with the energy in the form of photons of the universe, okay, density or whatever, what would I get? I would get 10 to the minus 10. The numbers relative, right? What is the energy of the baryon? It's its mass. The universe is very cold, nothing is moving, and anyway, these are guys in the star. It's GeV. What is the energy of the photon?
The temperature?
Is the temperature. Do you know this energy?
10 to the minus 4.
Yeah, it's around 10 to the minus 4 electrovolt. I think this is good enough for us, okay? If you were me, it's just for fun. So I get 10 to the minus 4 electrovolt. So this is 10 to the 9. So I get about 10 to the 3. Do you see this?
Yes. Yes.
Am I right? No. Yes.
In the bottom.
Minus 3.
No.
No, 10 to the 3. 10
Yeah.
to the 3 because this is 10 to the 9
Yes.
electron volt. So then to the 13 times 10 to the minus 10, 10 to the 3. So notice, it's full of, it's empty universe, but that emptiness is what matters, okay? So do you know how much dark matter there is in the universe? Well, it's about a factor of 10 of what baryons carry. Remember that roughly. This is why we speak of dark matter. It's bigger than what we see. It's strange. But we see only 10% of what is there. So what about the energy in the form of neutrinos? If I took the energy in the form of the neutrinos divided by the energy of gamma, I would normalize, the ratio is the same. So it will be mass of the neutrino divided by 10 to the minus 4 electrovolts. So what do I get? The neutrino mass is less than 1 Sorry?
What will you get for the neutrino mass?
Yeah, what should I put for neutrino mass? This is a
0.1 maybe?
about 10 to the minus 1 is where we are, if there's neutrino mass. So I get about 10 to the 3. Actually, I can put an upper limit on neutrino mass from there, right? If it's 10 to the minus 1 electron volt. So I get around the same for about an electron volt. I'll get to the same numbers for the number of variants. Okay. Not this extra factor of 10. There is something else in the universe. Anyway, we can stop on this note. This is why this is such an exciting topic.
Why do we need something else?
Because we need at least a factor of 10. For the dark matter, it's not what we see.